In this video, I'm gonna talk about some of the problems from problem number 10 onwards. And I probably can only recall until like problem 19 somewhere. Because first of all, I didn't do during the test, I myself didn't do the problems from 20 onwards because I didn't have time to do that. And I'm also not like that good. So um, I will just try my best to recall the problems. Um, the first problem, problem 10, I remember it's two cones. We have two cones, one with base 3, one with base radius 6. And both these cones are filled with water, and how much water we don't know, but we know that the amount of water in each cone is the same. And the question is asking if we put a unit cube into these two cones, these two containers, what is the ratio between the heights, the increase in heights for each cone container. Before doing this question, I would just like to point out a very interesting trick that you can use in multiple choices. If we observe this problem, one thing that they told you is the water in each container is the same. However, they didn't tell you how much, and they also didn't tell you the height. So that means how much water is actually in the container doesn't matter at all. So we can actually assume the amount of water to be 0, and we can kind of modify this problem a little bit. So if we could just change this problem into how what will be the height of the water if we put 1 unit cube of water into each cylinder. Immediately this problem becomes much easier because if you have a base 3 cylinder, then we have 1/3 times 3 squared pi times the height is equals to 1. And immediately we know that h1 refers to the height of this cone. And immediately we know that h1 is equals to 1 divided by 3 pi. And for this one, we do it in a similar fashion. And a very straightforward problem. We can already get that h1 to h2 is equals to 4 to 1. And it's basically as straightforward as that. So this is a very important skill that you want to use. You should always, instead of doing the problem directly by, for example, setting the water height in each cylinder as h1, and then you calculate the increase in the height, you should probably simplify the problem and see if there's any tricks. Like, for example, for this problem, we already know that the height of the water doesn't matter at all. So we can just assume it to be 0 to simplify the problem. The next problem is going to be 2 points of 3, 5, and 7, 5. So we have a ray shoots to the y-axis and bounces down from the y-axis to the x-axis and bounces back up. And we get from the coordinate 3, 5 to 7, 5 immediately. One thing to note is that the degree of these two angles are the same. So what we can do is simplify the problem by drawing actually a straight line reflecting 7, 5 across the x-axis to here, 7, negative 5, which will be something like this. And we keep the segment here. And we reflect 3, 5 across the y-axis to here, negative 3, 5. And we can use the distance formula to calculate the distance between these 2 points. This is the length of 5 minus negative 5 is equals to 10. This is 7 minus negative 3, also 10. So the distance is 10 root 2. It's as simple as that. For the next problem, it's not actually from problem 12 onwards, it becomes a little bit more difficult. For example, for problem 12, we have z to the power of 6 minus 10 to the power of 0, 10 times 0 to the power, z to the power of 5 plus az4 plus bz3 plus cz2 plus dz plus 16. So we want to find what the value of b is. And we know that z, the 6 roots of z are all integers. So if you guys learned the Vieta's theorem before, you know that this is the sum of roots and this is the product of roots. So if we express the sum of roots, we can express the sum of roots as this. No, actually simpler. We use mathematical notations. Is equal to 10, and the product will be 16. And we know that all 6 roots are the same. Not the same, sorry. All of them are integers. So what we can do is we can factorize 16, and we know it's 2 to the power of 4. And we know that the sum of these roots have to be 10. So if we can try 4, 4, 1, 1, 1, 1. That's obviously not 10. 2, 2, 4, 1, 1, 1. That's obviously not 10. So the only possible way is 2, 2, 2, 2, 1, 1. So actually, it doesn't matter which, like, if the first root is 2 or if the first root is 1, because it's interchangeable. Because what we're trying to find is the letter b. If you have learned the Vieta's before, the letter b is basically we have negative b is equals to sigma 1 smaller than I smaller equal to, sorry, smaller equal to I smaller than j smaller equal to 6 zi, sorry, I need to rewrite this again. Let me turn to a new page. So we have sigma 1 smaller equal to I smaller than j smaller than k smaller equal to 6 zi zj zk is equals to negative b. And immediately we know that we know z1 is z1. Let's say z1 is 2, z1 to z4 is 2, and z5 to z6 is 1. And we want to add like all of the combinations together. So first of all, the first combination is just 2 times 2 times 2. So what we get is C4 3, because we want to choose 3 numbers, and we have a total of 4 ways. So the sum is then 4 times 8. Because 2 times 2 times 2 is 8, and there are 4 combinations, so 4. The next combination is 2, 2 to 1. The 2 to 1, we can first choose 2 of the 4 twos. So we have C42 times we have 2 ones, so C21. So what we have here is 12, and 12 times 4 is 48. The last combination possible is 2, 1, 1. And what we have is basically we choose 1, 2 from the 4 twos we have here, and we also have we have to choose the only 2 roots that whose value is 1. So there are only 4 ways to do this. As a result, this is then 4 times 2 equals to 8. So we add the sum together, 32 plus 48 plus 8. Then we have 80 plus 8, so 88. So the final answer is b equals to negative 88. That's basically the answer for this problem. Number 3 is here. We have 5 answer choices. And we want to compare which one, when you do to the power of 5, is the largest. Immediately we know that this is a complex number problem. And when we have z to the power of 5, we have a complex number to the power of 5, it's usually not a good idea to do it in rectangular form. What I meant by rectangular form is if a complex, you can write a complex number in terms of a plus bi. And there's another form, it's called the exponential form, which is e to the power of I theta. And e to the power of, actually, sorry, we actually not e to the power of I theta, it's also r times e to the power of I theta, where r is the modulus, which is the length of the complex vector, and theta is the angle. So we can express complex numbers in these two ways. And when we have something to the power of 5, we usually want to convert from here. We usually want to convert from rectangular form to the exponential form. Oh, this is, by the way, this is also equal to r cosine theta plus I sine theta, due to Euler's formula. So we want to convert, basically we want to convert this. So let's convert this one by one. A is -2 times e to the power of I0. There's nothing, like, since it's only a real number, so we can just do it -2 to the power of 5, which we get -32. And for b, we have -√3 plus I. And sorry, I forgot to talk about this. If you want to relate the rectangular form to the exponential form, what you want to do is the r value is the modulus, which is root a squared plus b squared. And the theta value is arctangent b divided by a. That's basically the general formula. And if we have -√3 plus I equals to an exponential form, we can take the 2 out, which will become something like this. And if we draw a unit circle and the cosine value is negative and the sine value is positive, it will be something like here. And this will be 60 degrees. Sorry, this is not 60 degrees. This is 30 degrees. This is 30 degrees because this is a half. This is √3/2. So we know that this is e to the power of I 150, or you can say 5 pi over 6. That works as well. And for number 3, for C, we have -√2 plus √2i. And if you're familiar with these kind of numbers, you immediately know that's something about 45 degrees, because if you take the 2 out, it'll become something like this. And this is basically at this quadrant 2. So we have e to the power of I 3 pi over 4. And oh, sorry, I forgot to for this one, you also, like, when you do it to the power of 5, you basically do it the same, like you do it to the power of 5 for the modulus, and you times the angle by 5 times. So you have 32 times 25 pi over 6, which is basically I'm running out of space, which is So you have 25 pi over 6, and what you want to do is you want to minus 2 pi because any angle minus 2 pi returns the original value. So if you minus 2 pi here, then it will be 13 pi over 6. And basically, 13 pi over 6 is um, 13 pi over 6, we can minus 12 pi one more time. So we get this result. And if we expand it into the cosine and I sine form, we get root 3 over 2 plus half I. So real part will be 16 root 3. By the way, I forgot to tell you that when we're comparing in this problem, we're basically comparing which number's real part is the biggest. So we have 16 root 3 for B, and for C, negative root 2 plus root 2I, we have 2 to power of 2 times e to power of 3 pi over 4. So if we do that to power of 5, then it's 32 times e to power of 15 pi over 4, which is equals to 32 times e to power of negative pi over 4, because we minus that by 4 pi. And so 32 times the real part, 32 cosine negative pi over 4, it's the same as pi over 4 because it's a cosine's a even function, will be then 16 root 2. And for D, the number is negative 1 plus root 3I. We do in a similar fashion. And we do it in the same way. We get something like this. And this is, if you draw like a unit circle, this will be here. This is 60 degrees. And you can immediately eliminate this answer because you see the real part is negative. So obviously, like the other answer choices we have seen are all positive. So this one's definitely wrong. And 2i, you don't even need to convert it into the exponential form because you can just do 2 to the power 2i to the power of 5, and then this is like already like an imaginary number, which means the real part is 0. So the answer, if we look back at here, this is negative 32. This is also negative, so these two are out. This one's 0, this one's out, and this is 16 root 3, and this is 16 root 2. And obviously 16 root 3 is pure, so the answer is B. For number 14, this question is quite interesting because it requires a very kind of you have to be very familiar with logarithmic computations. So basically, it's here. Something like that, and you want to compute the value of that. There are some logarithmic identities I'm just going to go through real quick. So if we have log a b to the power of c, then we know it's log c times log ab. If we have log a to the power of c as the base and b here, then this is 1 over k times log ab. I'm not going to like prove or explain these identities until later videos because this is actually quite intuitive in the sense if we are talking about exponential functions. So we can use the same idea in these computations. So how do we simplify log 5k and 3k squared? We use these two formulas basically. And we can take the k squared out first. We're left with something like this. And we take the k out as well from the 5. So we have this equation. How about log 9k and 25k? We immediately notice that 9 is 3 to the power 2, so we can rewrite the equation as something like this. And interestingly, if we take 2k out from these equations, it becomes 1. They cancel each other out, in fact. So all in all, if we sub these two equations back in, we have sigma I equals to 120 and k log 5,3 times just sigma 1 I equals to 1 and 100 and log 3,5. So this is basically, you take the log 5,3 out, then we are left with an arithmetic sequence of difference 1, and that would be 20 times 21 divided by 2 times log 3,5, which is 100 log 3,5. And we know log 3,5 and log 5,3, they're basically reciprocals of each other, so we cancel them out. And we cancel this out, so we get 21,000 as our answer. For number 15, I couldn't really remember what the question was. It was something about tenors and basses, and you have to arrange them. I did it in a very, very kind of tedious and bashy way, so I don't want to present my solutions yet. So I'm going to do number 16 right now. So number 16 is basically you have this sequence of numbers. So if the number is 4, and if the number is n, then it appears n times. And the sequence stops at 200, 200, and 200. The question is asking for the median of this whole sequence of number. So what we want to do is we want to kind of find out which range of numbers that they're in. So basically we want to find out the total, how many numbers there are. And we know it's 1 plus 2 plus 3 plus 4 all the way to 200. And this is not hard to calculate. So we have a total of 20100 numbers. And the median will be that divided by 2. And sorry about that, 10050. It will be between 10050 and 10051, like the average of these two numbers. So basically our goal is to find out which number, like for example, if this number is 140 something or 150 something. So we basically want to see when we add these numbers all the way to some number, when will this be closest to 10050? So we can basically do it in this way. You can either try and error, which will take a long time, or you can do it we can do this method called the approximation technique. That's how I call it. And basically it's 20100 n times n plus 1. And you'll notice that, for example, if we sub in a random number 100 and 101, this is too far away, so we have to increase it, and 200 is too much. So we'll expect it to be in the middle, which will be around 150 times 151. In fact, 151 times 150 is, let me just calculate this real quick. 22350, and this is pretty close, but not there yet. So we decrease by 10, and if we do 140, we find out that this is actually really close, because if we look at this number, 20100, and this number, 19740, we immediately know that after 100, the last 140 is written, we move on to 141, and if we add 141, we just want to keep adding until we reach the point of 20100. Basically, that's I guess that's the solution for this problem. And I kind of forgot what my answer is, and I don't really bother to do it here, because it's a little bit arithmetically intensive, I guess. So yeah, and what I'm gonna do is I'm gonna move on to the last problem, which is number 18. Actually, I have two more problems. I will move on to number 18 first. Number 18 is basically FAB equals to FA plus FB, and FP equals to P only if P is prime. And obviously, if you look at this problem, it's a little bit it's a little bit weird, and you probably don't really have a good idea of approaching it. By the way, the question is asking which of the answer choices have fx smaller than 0, if fx is negative. And the correct answer choice should be, I think it's this. I don't remember the other answer choices, but basically, for this problem, what you want to do is you want to, like, you haven't been given any initial values, so you want to try out some values. So a one, like, really kind of obvious value you want to try is 1, because if you make both a and b are 1, then what you get is 1 times 1 equals to f1 plus f1, and f1 equals to f1 plus f1. Obviously f1 is 0, and this is like a very important initial value. After some time, you want to like kind of make use of this f1 value. So what you want to do is you want to make use of also the second condition. So we can do fp times 1 over p equals to fp plus f1 over p, and this is basically f1, and fp, we know that fp is what? We know that fp is basically p as indicated by the condition, and we don't know what 1 over f1 over p is. We know this is 0, so at the end we get f1 over p equals to negative p. This is very important, because if you look at the answer choices, I remember there are like, I think all the answer choices are fractions. So obviously you want to take the fraction part out. So I'm going to explain why 32 over 11 is smaller than why f32 over 11 is smaller than 0. So if we do this, we immediately notice that we can separate these two, and using the formula given in the condition, separate into these two expressions. And we know that f32 is 2 to the power 5, which is basically 2 times 2 times 2 times 2 times 2. And remember we derived that fp 1 over p is equals to negative p. So this is negative 11 right now because we know 11 is a prime number. And this is, since we know that f2 times 2 to the power 4 is 2 to the power 5, then we can do f2 plus f2 to the power 4, f2 plus f2 plus f2 to the power 3. All in all, we get 5 times f2 minus 11. And what is f2? Since 2 is a prime number, we can just do it. We can just make, we know that f2 is definitely equals to 2. So 5 times 2 is minus 11. 5 times 2 minus 11 is negative 1. Sorry about that. It's negative 1. So that's why it's negative. A very interesting problem, I'd say. And to be honest, like at first I didn't even realize how to do it, but like at the end I was like able to use all the conditions in the problem and kind of found the trick to the problem at the end. So very cool. And at last I remember this problem. I think it was problem 19 or 20. I kind of forgot. So it's basically like we have a function px or pz. I think it's pz. It doesn't really matter, to be honest. Pz equals to z to the power 3 plus az to the power 2 plus bz plus c. And the roots of this cubic function is cosine 2 pi over 9, cosine 4 pi over 9, and cosine 6 pi over 9. Sorry, not over 9. What am I doing? Over 7. And if you look at all of these three numbers, also we're finding for the value of the product of a times b times c. And if you look at these roots, they look really, really unpleasant because none of them are whole numbers. And even if they're whole numbers, we don't know the value of them. So we cannot really like bash it. Obviously, if you look at this problem, we're finding for a, b, c. And the first impression we get is, okay, so we know these roots. So we can just do sum of roots and use Vieta's, right? So obviously that was also what I thought as well, but only until after the test I realized there's a much concise way of doing it. Using Vieta's doesn't work, by the way. You might want to write it in this form. But using Vieta's is a good way to start. The thing is, you have to figure out what happens after using Vieta's. And negative c is just the product of all of them. Yep. And what do we actually notice about these three numbers? We notice that all of them are something divided by 7. And this kind of rings a bell about complex numbers, because if you actually do e to the power of I 2 pi over 7, then if you do that to the power of 7, it's actually equal to 1. And it's the same for cosine 4 pi over 7 and cosine 6 pi over 7. So we really want to make use of this fact. So let's start from z to the power of 7 minus 1 equals to 0. So z to the power of 7 is equal to 1, and 1 is e to the power of I0. Z to the power of 7 is equal to 0 to the power of 7. So what are the roots? According to the fundamental theorem of algebra, we know that there must be 7 roots. And you cannot really find the roots easily by just doing like the quadratic formula and stuff, because it's a 7th root function. So we want to use roots of unity. Roots of unity is basically when we look at the complex plane. This is imaginary, this is real, we want to split the circle into 7 equal parts, and we can find the complex vector for each root. And therefore, using roots of unity, we can get something like this. So if you look at this, we have 12 roots. 7 roots. And since we know all of these roots, what we can do is we can rewrite this equation in terms of root. So we can do z minus 1 times z minus, sorry about that, z minus e to the power of 2 pi minus 7 all the way to z minus e to the power of I 12 pi over 7. Using the, I think it was called the factor theorem, I kind of forgot. And if you note, I don't know if you noticed, but all of these roots, these 5 roots, are actually, they have a very, very interesting relationship with each other. If you just look at these two, and these two, they're actually conjugate of each other because, for example, for e to the power of I 2 pi divided by 7 and e to the power of I 12 pi 7, we can minus 2 pi because it's the same. And you know, when you see negative together, it means that they're conjugate because the cosine doesn't change, but the sign changes. So they're conjugate of each other. This rule applies to these two pairs as well. So what we can actually write is z minus 1, z minus, let's denote e to the power of I 2 pi over 7 as e, as epsilon. Then we can write it as this. Dash means conjugate. And if we see conjugates happening in a function, we always want to group them together, because if we group them together, we can eliminate the imaginary terms. And if we eliminate the imaginary terms, we'll be able to compute the value of the cosines, which are the real parts. So this is like all we're doing since from the start when we're doing z to the power of 7 minus 1 equals to 0, because we want to compute the values of, cosine 2 pi over 7 so that we can get a, b, c, and then we can find the final answer. And basically, if we times the conjugate together, and let's say we use, for example, for this one. Let's say, how do I do this? I'm going to denote, let's say, because we want to change it back to rectangular form. So I'm going to do something like this. It's just a symbol thing. It's not really important. Just to make it a bit clearer. And if we do this, then we can change this equation to, we group the conjugates together. We know that if we times the conjugates together, we get alpha plus alpha dash I times alpha minus alpha dash I, and alpha squared plus alpha dash squared. We times them together. If we add them together, then the imaginary parts cancel out and the real part remains. So this is z minus 2 pi, z to the power of 2 minus 2 pi z plus 2 alpha z, sorry, plus alpha squared plus alpha dash squared. And we know this is cosine something, this is sine something, so this is 1 basically. We simplify all the other as all the other terms as the same in the same method. What we get is this. And how do we proceed with this expression? If you remember, we have this expression. And remember the original equation for this function is z to the power of 7 minus 1 equals to 0. And we can factorize this by using the formula z minus 1 times z to the power of 6, z to the power of 5, z to the power of 4, z to the power of 3, z to the power of 2, plus z plus 1 equals to 0. And if we compare these two expressions, we notice that this part is the same as this part. So immediately we can notice this, how we can actually find the values for each of A, B, and C. So we want to find the individual value of A, like the alpha plus beta plus gamma equals to negative A. We want to find this first. So if we really want to find this, we want to compare the coefficients basically for each part. And if we want to compare the coefficients, the best way to measure alpha plus beta plus gamma is to compare the z coefficient. If we compare the z coefficient, then we take one z out from here, then we have to take one from here, or else there's no other combination. It's the same thing for this and the same thing for this. So what we get is negative 2 alpha z minus 2 beta z minus 2 gamma z is equals to 1, because the coefficient here is 1. Coefficient here is 1. And at the end, this is 1z, by the way. So z cancels out. And what we have is basically negative a half for alpha plus beta plus gamma. So A is negative a half, which is a half. How about for B? B is basically alpha beta plus alpha gamma plus beta gamma equals B. And let me just write out the previous equation first. So basically what we want to do is we want the alpha gamma beta together, we want the alpha gamma together, we want the beta gamma together. So what we can do is we can compare the coefficients for x squared. So we have to take x squared out from here. Like 2, let me just do it quickly. 2 alpha beta, 2 alpha, negative 2 alpha, negative 2 beta, x squared times 1 plus negative 2 beta, negative 2 gamma, x squared plus negative 2 alpha and negative 2 gamma together. However, we also have to know this is a little bit different because we also have another combination, which is x squared and 1, x squared 1, 1. So we have to add 3 because x squared times 1 times 1 and 1 times x squared times 1 and 1 times 1 times x squared is equal to x squared. And the x squared cancels out. So we have 3 over negative 3 over 4, is it? I think, yeah. So that's basically the value of, let me just write this out first. Yeah, that's basically the value of b. On to the last one. For the last one, we want to get alpha, beta, gamma. So what we want to do is we want to times these three together. So we have an x to the power 3 term and negative a alpha, beta, gamma. However, we have to notice that there are also other combinations for x cubed. For example, for x squared and x and 1. We have to count all of those. So basically we have minus 2 beta x squared minus 2 alpha x squared minus 2 gamma x squared. Yeah. However, we also have to note that there are multiple values for these, because if you can take 2 beta x from here and take x squared from here or x squared from here, so we have to times that by 2. All of this by 2. So what we have is this equation. Yep. And at the end, we compare this as x cubed, cancel out the x cubed. Then we have 1 over beta plus alpha plus gamma. And this is alpha, beta, gamma. And yeah, and then, sorry, this is negative. And if we look back, alpha, beta, gamma is basically here, is negative of half. And if we go back here, this is negative of half times negative of half. And this will be sorry, I made a mistake. This is a bit annoying. I made a mistake. Sorry about that. So basically what we have here is 1 plus 4 beta plus alpha plus gamma. This is negative 8 alpha, beta, gamma. And 1 plus 4 times negative a half, which is negative 1. This is negative 8. So alpha, beta, gamma will then be 1 over 8. And this is it. And often these always happen. When you do a problem, you always kind of make careless mistakes, just as how I did. Also for this problem, because I assumed the right hand side is 0, but in fact it's 1. So I have to change all of this. This is basically negative 2. And this is a half, negative a half. And for this one, it's 1 over 8. But if you look at this, it's I basically also assume that the right hand side is 0, and in fact it's 1. So all of you guys have to be really careful. So at the end, what we have is we have alpha plus beta plus gamma as negative a half, which means a is a half. Alpha beta plus alpha gamma plus beta gamma as also a half, I think. negative a half, in fact. So b is negative a half. And finally, c is basically the product, which is negative 1 over 8. Sorry, not negative 1 over 8. It's just negative 1 over 8. So at the end, we have a, b, c equals to 1 over 32. And that's it. I know like this is my way of doing it, using complex numbers. I'm not sure if there's like any other, more concise ways of doing this. So yeah, so that's my take on AMC12 for now. After the official problems are solved, I will also try to solve the ones like from 20 onwards, but like they will be probably more difficult. So you guys can actually go to our problem solving and look at those solutions. So yeah, I hope you enjoy my video. I know it's a bit cringe, but like it's my kind of like my second video on this channel. So yeah, hope you guys enjoy it. I'll see you next time.